Exactly. Thank you very much for the introduction. I'm a member of the research unit of Advanced Composite Nanomaterials and Nanotechnology. And this study was part of a national program about antifouling paints that was named Marie Paints. The outline of my presentation. First of all, I will define the goal and scope. I will give a short introduction about the coating systems currently used in maritime industry. Following, I will describe some things about the carbon nanotubes that are named CNTs, especially about their synthesis and functionalization process. I will give details for the experimental procedure that was followed for the coatings preparations that included the substrate preparation, the coating synthesis, and the application. And finally, I will give the results about the nanomechanical and electrochemical characterization of the samples. The main objective of this work is to propose the most efficient coating system in terms of both mechanical and anti-corrosion response. The special goals were the synthesis of multi-wall CNTs with different surface functionalization for improved compatibility with the coatings matrix. Also, it was important to incorporate the CNTs in both epoxy primer and anti-fouling top coat paints in various concentrations in order to find the optimum concentration for the best nanomechanical and electrochemical response. The investigation of their nanomechanical and electrochemical properties via nanoindentation technique and electrochemical impedance spectroscopy were executed respectively. The engineered structures, such as ship hulls and marine platforms, are under contact attack from the aggressive marine environment. The severe environment, in combination with the problem of fouling, contributes to the enhancement of corrosion phenomena, and as a result, we can have this kind of surfaces that need treatment. This is a picture that represents the fouling process over the ship hulls that contributes to the corrosion. In order to deal with this problem, organic coatings are commonly used for the protection of the metallic parts of the ships. The most currently used coating system is a system that combines epoxy-based primer, anti-corrosive barrier coat, and finally an anti-fouling top coat. Carbon nanotubes are an advanced material that has been developed in the last decades, and they consist of graphitic filaments with diameters ranging from 0.4 to 500 nanometers, a length up to several hundred micrometers. Their structure is presented at this photo. CNTs are one of the most strongest materials in nature, exhibiting elastic modulus of about 1 terapascal. They also exhibit extraordinary electrical conductivity. That means that they can be used also for electronic applications. So they can be considered as ideal candidates for polymer reinforcement. They can also lead to the improvement of the mechanical and electrical properties of the produced nanocomposites, and for this reason they can offer mechanical integrity to the antifouling coatings. Here we can see some of the applications of carbon nanotubes in microelectronics, biotechnology, environment, energy storage, and that in which we are concerned, coatings and films. The carbon nanotubes were produced in our study through the chemical vapor deposition method. It is a method that we use a tubular furnace that can raise temperature up to 1,200 degrees. As precursors, they can be used solids, liquids, or gases. And in our case, we used as a solid precursor camphor in combination with ferrocene, that it's the appropriate catalyst. The CNTs can be grown up on quartz or silicon wafers. At the CM image, we can see the produced CNTs that are synthesized in a structure of carpet, and in higher magnifications, we can see that CNTs are like small wires, like a small spaghetti. The well dispersion of CNTs into polymer matrices is critical for the improvement of the composite properties. That's because we have strong attractive non-covalent forces that are developing between the individual CNTs due to their huge aspect ratios. These forces lead to low interactions between CNTs and polymer matrices and can lead to the aggregation into bundles. So in order to improve the dispersibility of CNTs into the polymer matrices, surface functionalization of CNTs is needed. By the surface functionalization, we can add active groups on the sidewalls of the CNTs in order to improve their compatibility with the polymer. In this study, we tested two different functionalizations. The first one was the adding of carboxyl groups on the sidewalls of the CNTs. The procedure that took place was this that is described in the flowchart. And a very important step was the acid mixture of sulfuric acid and nitric acid in a ratio 1:3 that enables the addition of the carboxyl group on the sidewalls of CNTs, as you can see in the schematic representation. The other functionalization that took place was the functionalization with the amino groups, in which we used the already synthesized carboxyl CNTs, this with the carboxyl group, and we tried to add an amino group, an amine, using thionyl chloride and this procedure. The critical step in this reaction was the addition of ethylene diamide at 100 Celsius for 2 days. The results of the functionalization can be observed by the FTIR spectra, in which we can observe a new peak that appears at 1564 wavelengths, which can be assigned to the nitrogen-hydrogen in plane. Also, we can observe from the SM image that the functionalized CNTs have this kind of morphology, and they have diameters in a range from 20 to 40 nanometers and the length over 10 micrometers. The FTIR spectra shows that the functionalization was successful and the amino groups were grafted on the CNT sidewalls. After the synthesis of the carbon nanotubes, it was important to produce the coating. For this reason, we used, first of all, substrate that was hot-rolled steel shipbuilding plate grade A, and we treated its surface according to the ASTM A380-06. For the synthesis of the composite coating, we used a high shear mixer with a velocity of 2,200 RPM, in which we combined the produced and functionalized CNTs with a coating. For the application, we used a dip coater, and for the estimation of the dispersion, we used a dispersion gauge, and we estimated a dispersion from 30 to 40 micrometers. All the samples that were produced are included in this table. We had two reference materials, just one epoxy primer, and another reference system with epoxy, anti-corrosive, and anti-fouling paint. We produced 4 different samples of epoxy with different concentrations of the carboxylated multi-wall CNTs, and 3 different anti-fouling coatings with the same concentration of CNTs, but using CNTs with different functionalizations. After the preparation of the samples, the nanomechanical and electrochemical properties were tested. For the nanomechanical properties, we used a nanoindenter. Nanoindentation system can determine the mechanical properties of a material, such as strength, toughness, surface adhesion, and creep, as well as we can observe some effects like pile-up and sink-in, or determination of the actual 0 point. This technique can be also combined with scanning probe microscopy or atomic force microscopy in order to evaluate the surface morphology. We can also determine the real area of contact with nanoscratch tests. The nanoindentation technique is the most suited method for studying the local mechanical properties in a small volume of a composite material. We use a tip of a known geometry that indents in the surface of the sample by a standard load, whereas the penetration of the indenter tip into the sample surface is continuously recorded. As a result, we have this load and load curves, from which we can determine the elastic modulus and the stiffness of the material using the slope of the initial part of the unload curve. After the calculations, we can calculate also the elastic modulus, stiffness and hardness of our material using the Oliver-Farr model. The results of our study were that the addition of low concentrations of multi-wall CNTs with the carboxyl groups results in similar plastic behavior and resistance to the applied loads with a pure formulation coating. So we didn't observe any difference, as you can see from this chart. Medium concentrations led to a significant improvement of the resistance to applied loads. That means that we have a threshold concentration for the 0.2 percentage. Finally, the higher addition of multi-wall CNTs with the carboxyl groups resulted in softening of the material, as you can observe from the last column. About the antifouling coatings, we had different results. Firstly, the addition of the 0.1 percentage multi-wall CNTs with the amino functionalization resulted in slightly higher resistance to the applied loads compared to the reference sample. That means that we have an improvement on the mechanical properties of this coating. Also, the incorporation of the same material in antifouling top coat improved significantly its mechanical performance, having an increase of around 30% of the hardness and 15% of the modulus. Whereas the samples 1 and 2 presented lower reduced modulus by around 30%. That's why we have not very good compatibility between the carbon nanotubes and the polymer matrix, if they are pristine or if they have the carboxyl functionalization. Also, we performed the electrochemical testing using the electrochemical impedance spectroscopy, which is one of the most suitable techniques to follow the evaluation of the corrosion rate because it's not a destructive technique. The usefulness of the impedance spectroscopy lies in the ability to distinguish the dielectric and electric properties of individual contributions of components under investigation. To perform the measurements, an electrochemical cell is needed, and we use 3 different electrodes: a working electrode, a reference electrode, and the counter electrode. The results of the electrochemical testing were that the addition of the CNTs degraded the corrosion resistance of the epoxy primer. This can be seen from the body plots here. So it's not recommended, finally, to use the CNTs in the epoxy primer, while they may have, there may be giving some extra conductivity to the polymer matrix, enabling the corrosion phenomena to accelerate. Also, about the antifouling performance, the electrochemical performance of the antifouling coatings, we observed that the addition of CNTs didn't affect their electrochemical performance. From these plots, from these plots, we can see that all coatings are performing like capacitors. So to conclude, the influence of multiple CNTs addition in both epoxy primer and antifouling top coat layers were studied. To achieve a homogeneous dispersion of multiple CNTs in polymer matrices, we used different surface functionalizations, and they were applied on CNTs. The incorporation of carboxyl functionalized CNTs in the epoxy primer led to increased hardness values for the concentration of the 0.2%, but deteriorated its anti-corrosion performance in all cases. Also, the presence of the amino-functionalized CNTs in antifouling top coat improved significantly its mechanical performance without any effect on its anti-corrosion behavior. So, if we would like to conclude to a specific system, the proposed antifouling paint system can be consisted of an epoxy primer layer without CNTs, an anti-corrosion intermediate layer, and finally an antifouling colophony-based top coat, a CDP system as was referred to before, containing 0.1% of the amino-functionalized CNTs. So this system can provide both improved mechanical integrity and acceptable anti-corrosion behavior. Thank you very much for your attention, and I'm open for your questions.
Thank you very much about this nice presentation.
Any questions?
Do you have any questions?
Please.
Yes?
Have you studied the effect of roughness?
We have also made a lot of measurements with optical microscopy or with nanoscratch test about the roughness of the coatings. It is very crucial to see the roughness. When we had the concentration of the 0.4% of CNTs, the roughness was very increased, and this is why maybe we have also problems with anti-corrosion performance. The concentration of the 0.2% was the ideal. We had a very nice dispersion of the CNTs. The surface was really smooth, and it was very nice, the results. And we used optical microscopy and the scanning probe microscopy for the estimation of the roughness. I'm really not remember right now, but I think that it's. No, I will give you the details better afterwards because I don't remember the exact number, but I have noted. Yeah. Mm-hmm. Yes.
Are there any plans in your research that you may see the real-time effects when the ships out?
Yes, this study is part of a national project that is ongoing, and the point is to see how the scientists can improve the mechanical performance of these coatings in order to last longer. As it was mentioned in the first presentation, controlled plate systems have a lifetime about 3 years. We believe with the reinforcement with CNTs, we can extend the lifetime of the coatings, and we're trying to check their performance under shear stresses, under friction, etc. So this is the final goal of this project. Mm-hmm. Yes?
For the best performing configuration you showed about the amino
Functionalization.
You started to show there, I think that there was a step that lasts for 2 days. That is the one that you mentioned also that is a very important step. About this, is it possible to speed up this process in order to be able also to upscale this method?
Yes, this is what we are trying to find. Unfortunately, to perform the reaction, we used also really 2 days. It cannot be speeded up this time because it's a very difficult reaction to be achieved. The production of CNTs, on the other hand, can be scaled up, can be easily scaled up. We can produce at this time around 10 grams per batch. It's in the lab scale, as you can understand. But the functionalization process, it's a little bit difficult to be upscaled. Also, another problem is the thionyl chloride that we use, that it's very difficult to handle. So I think that we have to find another way to functionalize with the amino in order to have the scaling up.
Can you try to make this reaction with a lot of layer effect, increase pressure or something like that?
No, not really. It's only
degrees, but
we have a reflux.
okay.
A reflux.